Welcome to today's class on graph theory. Today we discuss non-Hamiltonian planar graphs and we prove Grinberg theorem in this class. Tate in 1880 showed that four-color conjecture to be equivalent to the statement that every three-connected cubic planar graph is three-edge colorable. Tate thought that he had thereby proved four-color conjecture because he believed that every such graph was Hamiltonian and hence three-edge colorable. Tutt in 1946 showed that this is to be false by constructing a non-Hamiltonian three-connected cubic planar graph. For many years, Tutt graph was the only known example of a non-Hamiltonian three-connected cubic planar graph. So the following graph is Tutt graph. But then Grinberg in 1968 discovered a simple necessary condition for a plane graph to be Hamiltonian. His discovery led to the construction of many non-Hamiltonian planar graphs. Now we discuss Grinberg's theorem. Now we state the Grinberg's theorem. Let G be a loopless plane graph with a Hamilton cycle C. Then sigma I is equal to 1 to nu I minus 2 into phi I dash minus phi I2 dash equal to 0, where phi I dash and phi I2 dash are the numbers of faces of degree I contained in the interior of C and the exterior of C respectively. And this equation sigma I is equal to 1 to nu I minus 2 into phi I dash minus phi I2 dash equal to 0 is known as Grinberg's identity. So now we prove the theorem. Proof. Denote by E dash the subset of E of G minus E of C contained in the interior of C. And let epsilon dash equal to cardinality of E dash. Then interior of C contains exactly E epsilon dash plus 1 faces. For example, you can consider this graph. So this is the Hamilton cycle C, which passes through all the vertices of the graph, and we have E dash is the edges in the interior of the cycle C. So 1, 2, 3, 4, 5, 6. These 6 edges belongs to E dash, and epsilon dash is the number of edges in the interior of C. So it is a 6, and you can observe that interior of C contains 6 plus 1, 7 faces. So 1, 2, 3, 4, 5, 6, 7 faces. So it contains exactly epsilon dash plus 1 faces. Therefore, sigma I is equal to 1 to nu phi I dash is equal to epsilon dash plus 1. Now you can see that so each edge in E dash is in the boundary of two faces in the interior of C. So you can see that this, for example, this edge is in the boundary of this face and this face, and similarly you can see that this edge is in the boundary of this face and this face. So each edge in E dash is on the boundary of two faces in interior of C. Also you can observe that each edge of C is on the boundary of exactly one face in the interior of C. This is an edge of the cycle C, and you can see that it is on the boundary of exactly one face, and each edge of C is on the boundary of exactly one face in interior of C. Therefore, sigma I is equal to 1 to nu I phi I prime equal to 2 epsilon dash plus nu. This is equation 2. You take this as equation 1. Now from 1, epsilon dash is equal to sigma I is equal to 1 to nu phi I prime minus 1. So substituting this, you take this as equation 3. Substituting 3 in 2, we get sigma I is equal to 1 to nu I phi I prime. This is equal to 2 times sigma I is equal to 1 to nu phi I prime minus 1 plus nu. So this implies sigma I is equal to 1 to nu I phi I prime minus 2 into sigma I is equal to 1 to nu phi I prime equal to minus 2 plus nu. This implies sigma I is equal to 1 to nu I minus 2 into phi I prime. This is equal to nu minus 2. This is equation 4. Now by similar arguments on exterior of C, we get similarly sigma I is equal to 1 to nu I minus 2 into phi I 2 dash equal to nu minus 2. This is equation 5. Now 4 minus 5 implies sigma I is equal to 1 to nu I minus 2 into phi I dash minus phi I 2 dash. This is equal to 0. So this is known as the Grinberg identity, and this proves the theorem. Now using this theorem, we are going to show that the Grinberg graph as shown in this figure is non-Hamiltonian. So example, the Grinberg graph is non-Hamiltonian. Solution. From this figure you can see that this graph has only faces with the degree 5, degree 8 and degree 9. So note that the Grinberg graph has faces of degree 5, 8 and 9. So by Grinberg's identity, we have sigma I is equal to 1 to nu I minus 2 into phi I dash minus phi I 2 dash equal to 0. So this graph has only faces of degree 5, 8 and 9. So I is 5, 8 and 9. So this implies 5 minus 2 into 5, 5 dash minus 5, 5, 2 dash plus for degree 8, 8 minus 2 into 5, 8 dash minus 5, 8, 2 dash plus 9 minus 2 for faces of degree 9. It is 5, 9 dash minus 5, 9, 2 dash. This is equal to 0. So this implies 3 into 5, 5 dash minus 5, 5, 2 dash plus 6 into 5, 8 dash minus 5, 8, 2 dash plus 9 minus 2, 7 into 5, 9 dash minus 5, 9, 2 dash. This is equal to 0. Now taking modulo 3, you will get, so this implies this is a multiple of 3 and this is a multiple of 3, so that gives 0 taking modulo 3. So this implies 7 into 5, 9 dash minus 5, 9, 2 dash. This is equal to 0 mod 3. And from the graph, observe that there is exactly one face of degree 9. Either it is an interior face or it is an exterior face. If it is an interior face, phi 9 dash is 1 and phi 9 2 dash is 0, because there is only one face of degree 9. And if this face is an exterior face, you have phi 9 dash is 0 and phi 9 2 dash is 1. So in that case, you are getting either 7 is congruent to 0 mod 3 or minus 7 is congruent to 0 mod 3. That is wrong, because 7 is not a multiple of 3. So this proves Grinberg graph is not Hamiltonian. So if it was a Hamiltonian, this must be equal to 0 mod 3. So which is impossible, since if the face of degree 9 is in interior of C, then phi 9 dash is 1 and phi 9 2 dash is 0. So in that case, from this equation, double star 7 into phi 9 dash 1 minus 0 is equal to 0 mod 3. So this implies 7 is congruent to 0 mod 3, which is wrong, which is not possible. Now if the face of degree 9 is in exterior of C, then phi 9 dash is 0 and phi 9 2 dash is 1. Therefore from double star we have minus 7 is congruent to 0 mod 3. So which is also not possible. Therefore the Grinberg graph is not Hamiltonian. Hence the Grinberg graph is not Hamiltonian. So that's all from graph theory. Have a nice day.